Hello, hi, welcome to Teach You Why. This is a channel aimed to help students with their upcoming O-level pure physics paper. This video is created for our students specifically for our student in Singapore. But if you are from any other countries or region watching this, I hope you will find this helpful for your revision as well. So today I'll be going through the 2020 ACS Barker Prelim paper for pure physics. The link to download this paper is as shown in the description below. Feel free to check it out, and without further ado, let's get started. So let's take a look at the first question. So the first question shows that a man cycling forward on a straight road with a surface P. After cycling for 10 seconds, he enters a road surface Q. Throughout the entire journey, the man exerts a constant forward force forward. So this is my keyword, constant forward force forward. So let's draw a little bit of free body diagram. Force is equals to 600 Newton. And so in figure 1.2, it shows a resistive force on the bicycle against time. So we can almost imagine that the road here, okay, it has some resistive force. So let's call it friction. All right. Okay, so let's see part A. Describe the acceleration of the bicycle from t equals to 0 to t equal to 20 seconds. So in order to solve this, let's take a look at so from the free body diagram we can see what is the net force exerted, what is the net force on the bicycle and the cyclist. So the net force will be equals to 600 Newton, which is the forward force, minus the friction. Now where is the friction? The friction is here. All right, so here to here, and we have the other portion here to here. So as you can see, between 0 to 10 we have a constant resistive force, which means that from t is equals to 0 to t equals to 10, the net force will be equals to 600 Newton minus 220 Newtons. All right, which will give you 580 Newton constant. All right, so what does this mean? This means that we have a constant acceleration during this period. All right, so in this case my answer will be between t equals to 0 to t equals to 20 to t equals to 10, the cyclists have a constant acceleration. Now, how about the other part between, because the question asks for from 0 to 20 seconds, how about the other part? So between 10 to 20 seconds, you can see that the friction is increasing, which means if based on this equation here, we know that if my friction is increasing, my F net will be decreasing. And likewise, if my F net is decreasing, F net decrease, it will cause my acceleration to decrease. So then we will need to say that from t equals to 10 to t equals to 20, the cyclists have a decreasing acceleration. Okay, so that's how we analyze this question. Now calculate the acceleration of the man and his bicycle at t is equals to 5. All right, so that means where we want to look at somewhere here. All right, so around here t equals to 5, my resistive force is still 20, and therefore in order to find the acceleration, F net equals to 600, which is your forward driving force, minus your friction. Okay, and then so to find your acceleration equals to F net over mass. Okay, and therefore is 600 minus 20 over my mass is 150, and we will get hold on a second. Okay. Okay, we will get 3.866 meters per second square. So 3 sig fig will be 3.87 meters per second square. Okay, 3.87 meters per second square. All right, so calculate the speed of the bicycle at t equals to 10. So we recognize that between here to here, right? Between here to here, we have a constant acceleration. All right. So then, to find the speed, we will use this formula. V equals to U plus AT. Now, where do you get this from? We derive this from this formula. V minus U over T basically is your final velocity minus your initial velocity over time is equals to acceleration, and we have already found the constant acceleration, so right now we can find the final velocity when t is equals to 10 seconds. So v is equals to, what's my initial velocity? My initial velocity is 2, so 2 meters plus 3.87 t. Alright, so we get an answer 3.87 times 10 plus 2. Okay, we get a speed of meters per second. Alright, we get a speed of about meters per second. Alright, so this is my answer. Okay, moving on to the next question. Now, this question, when we take a look at, it says that it has a uniform rectangular block on a flat horizontal surface. And then the force F acts on a block in this manner, and then it tilts the block about point H. So this is like your pivot, which means that this block will be rotating in this manner when you exert a force, because it's like a pivot and then you rotate. Now, so let's take a look at part A. On figure 2.1, mark with a cross X the position of the CG of the block. Now, since this is a uniform rectangular block, you can almost treat this as like a center. So we can basically split into two parts. Okay, so you assume that this side here is equidistant, this part here is equidistant, and therefore this is my answer. Okay, it's right at the center. Now, in the space below, draw the diagram to show how far the block can be tilted about just before it topples. So this is the key point, just before it topples. It means that a little bit more and then it will rotate all the way, but it shouldn't go all the way. All right, so let me try my best to draw this. So we have something like this. Okay, not too great. Let me try again. Okay. Okay, this is more like it. So it's somewhat here. No, no, not too great. Somewhere here. Okay. Okay, let me erase this. It's not too good. So we have somewhat like this, like this, like this. Can should be here. Yeah, this is good. Okay, so what this means? This means that, right, so this is where the CG, this CG is just right at the point acting in the direction of the pivot B. So why is this the answer? Because if my CG is slightly to the right here, can you see that it creates this moment arm that will rotate this block over? Okay, so but if it is slightly to the left, right, then again it will create, you can see, almost see like this, there will be a moment arm created that will rotate the block and anti-clockwise, all right, and then go back to its original standing position. So this is my sketch, and this will be the answer. Okay, so you need to make sure that the CG is right at the center, right in the line of point B, which is why I was struggling to draw it freehand without any ruler. Okay, state and explain how your answer in B will differ if the height of the block is to be reduced. Now, what happens when we reduce the height? So let me erase this. So if let's say I have a shorter height, okay, but same base length, so same thing, we cut into half. What do you notice about the CG? Can you see that the CG has lowered, right? So my CG has lowered. Now, so if my CG has lowered, it means that this block in red, the shorter height block, is more stable. Lower CG, higher stability. All right. So what this means is that now, so let's say this is anchor data. So how will your answer in B differ if the height of the block is being reduced? So the angle of tilt will be greater as the reduced height block is more stable. Okay, so which allows it to be tilted more before toppling. Okay, hope you guys understand what it means. Okay, moving on to the next question. Now this question, what is my thought process whenever I look at this diagram? Now this topic will definitely be on pressure. So when it comes to pressure, then you need to think of when you see mercury and you see a barometer like this or manometer like this, you straight away you think of hydrostatic pressure. So hydrostatic pressure, okay, is equals to rho GH. Alright, so in a short while I will analyze this question. So the question asks for calculate the pressure of the air in the flask. So why is there, so in this case there is a flask here, so pressure in the flask act in all direction, okay, and then some part of this can also act pressure onto this part of the fluid of the mercury, and from here we will draw a datum line across. Now what does it mean by a datum line? Datum line means that the pressure here, let's call this P1, and the pressure at P2 is the same. Alright, so we will we'll represent it as P1 is equals to P2. Now, what is P1? P1 is basically your pressure in the flask, so there's nothing to talk about. Now, how about P2? Now, if you take a look at P2, we have an atmospheric pressure, okay, pressing down, and then at the on top of it, you also have a hydrostatic pressure that is due to the mercury column here, this height here, and therefore we will say that is P2 will be equal to P atmosphere plus rho GH mercury, okay, and therefore we will have, this is my atmospheric pressure plus rho GH, rho, this is my density 13600, gravity is 10, my height. So now in this case, the height, you need to take a look at the height at this point, okay, from the surface. So let me just estimate and have a look. So it's approximately 380. So the height will be 380 minus 200, right? Basically, we want to know the length of this point here, right, over here, and because this is mm, so we need to be careful, mm, so it's times, okay, so let's find the answer. So we have 3600 times 10 times 380 minus 200 times 3, so you get 1.0 times 10 to the power 5 plus 24480 PA, and then you add these two up at the power 5. 1.2448 times 10 to the power 5 PA. Alright, so 3/6 feet, the answer will be 1.24 times 10 to the power 5 PA. Alright, 1.24 times 10 to the power 5 PA. So this is the answer. Alright. Now, the difference in mercury height decreases as the air in the flask starts to cool, which means that this flask, the temperature starts to drop. Now, what happens when temperature drops, and how the temperature will somehow affect the height of this column? Okay, so let's recall what we learned in kinetic particle theory. So in kinetic particle theory, we know that when temperature increase, it causes pressure to increase. Now, why is that so? So let's take a look. Now, as temperature increase, right, it causes the air molecules to have increased Ke. And now when the Ke increase, this means that the force per collision increase. That's point number one. And then it also affects, because my K increase, right, it also means that the frequency of collision also increase, right? That's when my temperature increase, my K increase. Now, maybe I explain a little bit more. Why K increase will cause force per collision to increase is because Ke means that how fast the air is moving. So which means that if my K increase, my air particle is moving faster. Therefore, the force per collision will be higher. The frequency of collision will be higher. Okay, so with this knowledge, we will apply it onto this question. But this question is the opposite. In this question, we are talking about when T decrease. So we will explain in a reverse manner, right? So what we will say that when temperature of the air in the flask drops, okay, the pressure, no, let's not go into there. This reduces the KE of the air in the flask, and therefore pressure, no, we cannot say that. We need to say that the force per collision decrease and frequency of collision decrease. All right, now let me pull this down because it's a long answer. Now, so then therefore pressure will drop, hence the mercury column height will also fall. Okay. Okay, moving on to the next question. Whenever we see question like this, straight away we know this topic is on energy, work done, etc. How I know is quite obvious. When you have high, you have a ball. Pretty sure that this will represent a GPE. Okay, so we start off with a definition question. Okay, before I will analyze the question in a short while, but since part A is just a definition question, so define work. So what is work? Work is the transfer of energy to an object traveled in the distance exerted by a force. All right, I wouldn't explain too much of this definition. You can look it up on your textbook, right? Okay, so let's take a look at this question. Calculate the speed of the ball at position C. So we want to know the speed here. Okay, now how can we relate? So in this case, we will need to make use of the laws of conservation of energy, right? So, and what does laws of conservation of energy represents? It says that the total energy of the system before and after has to be the same. All right, which means that this is before. So at point A, this is what we define as before, and at point C is after, right? Before and after, the system must have the same amount of total energy. It doesn't matter whether is it kinetic energy, potential energy, as long as the sum of all energy must be the same. So we will use this approach to solve for this question. All right, so in this case, the question also says that the air resistance is negligible, which means we no need to care about any work done against air resistance or friction, because it also says it is a smooth ramp. That means there is no friction here. Okay, so we can safely say that at point A, so let's find the total energy at A must be equal to total energy at C, right? So what is my total energy at A? So total energy at A will be you have your GPE, which will be equals to Uh, Okay, so in this case, we don't know the mass, but we can still solve it. I will explain in a short while that the mass here doesn't affect, regardless of what mass this ball is, it doesn't affect the final velocity. All it cares is the energy, is the height that will affect the final Ke. Why is that so? It's because mgh, okay, GPE will be converted into Ke, which is equals to half mv squared. All right, so you can see that both end we have this m that will cancel out one another, and then when we rearrange the equation, we'll realize that v is equals to square root 2gh. All right, so this means that velocity, the change in velocity, is a function, or it is proportional to the height and then the gravity only. It doesn't matter what is the it is independent of the mass of the ball. Okay, so in this case, we can find, so in this case we know that the total energy at point C will be only Ke. All right, so let's first find what is the change in Ke due to the change in GPE. So that means as the ball rolls down, it is reducing GPE. GPE is dropping, and then at this point, you have no more GPE, and all the GPE is converted into Ke. So in this case, we will use this idea. So GPE equals to change in GPE equals to change in Ke. Therefore, mgh is equals to half mv square, and therefore v is equals to square root delta v, delta v is equals to 2gh. And then what is my height? My height is 12, my g is 10, so 2 times 10 times 12. And then let's see what we have. 12 times 10 times 2 square root 240, you get 15.9. okay, so but this is the change in velocity. Now, because the ball have an initial velocity of 5 meters per second, so the final velocity is equals to 5 plus this. Okay, and then we get 20.49, which is equals to 20.5. okay, 20.5 meters per second. All right, so this is the answer. Now the ball continues to roll from C until it stops at E. All right, so it will roll up and then it stops here. How it stops here, I'm not too sure. It feels like it has some sticky tape here, but okay, since the question says that, we will leave it as such. Right, so calculate the total work done against friction by the ball along CDE. Okay, so now so how do we, hold on, total frictional force. Oh, sorry, they already gave us. Sorry, I wasn't reading the question. So the ball continues to roll from C until it stops at E. The total frictional force along CDE is 10 newtons. So work done against friction. So work is equals to force times distance. So since we already have the force, so it's 10. What is my distance? Okay, from CDE. So CDE, the distance is 2 plus 8. So times 2 plus 8 equals to 100 joules. Okay, 100 joules of work done is this is 100 joules of work done. Okay, now the total energy at the ball at any position between B to C is 265 joules. So between B to C, okay, B to C, like we say, B to C is 265, sorry, 265 joules. All right. Calculate the total energy the ball possess at E. Okay, so now, we will use conservation of energy, which means that at point E, point C must be equals to point energy at point C must be equals to energy at point E. Okay, so we need to account for all the energy loss, or basically we need to account for all the energy it possesses and all the energy it has lost to the environment. So the energy at point C is 265. Now the energy at point E will be energy the ball has. So energy total E and okay, plus the work done against friction. Okay, so total energy at E will be equals to 265 minus my earlier solution 100 joules. So you get 165 joules. All right. Assuming the path CDE is now smooth, mark with a cross X on figure 4.1 to indicate the possible new location where the ball stopped. Okay, so it's a bit messy here. So assuming that between here to here, it is now frictionless. All right. So where do you think the ball will stop eventually? The ball can actually stop higher than this point. Now, so this is my answer. Okay, so this is where the ball will eventually stop. Now, why is that so? It's because since if no energy is lost along the path here, along the path all the way here throughout, which means that all its GPE can be converted to KE down here and then go back to GPE. Now, how come it can go further up? It's because it initially has some kinetic energy which this KE here is able to further convert the KE into additional potential energy, and therefore the final position, okay, if there is no friction, it is this point. Okay, all right, moving on. Now a thermocouple gives a reading of 5.0 millivolts when the cold junction is placed in melting ice and hot junction is placed in steam. The cold junction is now placed in a liquid of an unknown temperature and the hot junction is left in the surrounding air. The thermocouple gives a reading of 3.0 millivolts. Explain why potential difference measured above is not useful in identifying the temperature of the surrounding air. Now, what do we need to know is that how a thermocouple works is that it measures the temperature difference between the 2 points. Now, so the first part here is to calibrate. Now, what is meant by calibrate? So you see, my cold junction is placed at melting ice. So we need to recall that melting ice is at 0 degrees Celsius, and then the hot junction is placed in steam. Steam is 100 degrees Celsius, which means that if my temperature difference is 100 degrees, will give rise to a reading of 5.0 millivolts. Okay, so you need to have this idea that the thermocouple is only able to measure difference in temperature. Okay, so this is a difference in temperature. Now explain why potential difference is not useful in identifying the temperature of the surrounding air. Now you see, now we have a case that the hot junction is maybe in a liquid, okay, and then maybe the other junction is now in the air, okay, air. So the problem is that even though we know that it's 3.0 millivolts, given that we also don't know this temperature, how can we measure the temperature of air? So the only thing that we know here is that the temperature difference between the liquid here, okay, this liquid here, and the temperature in the air is that will give you a 3.0 millivolts. So therefore, why is it not useful is because the temperature of the liquid is unknown, okay, then the 3.0 millivolts only represents a 60 degrees Celsius temperature difference. So we only know that there is a 60-degree temperature difference between the liquid and then the air. But since we don't know the temperature of the liquid, we are unable to work backwards to find the temperature of the air. So in other words, temperature of the air minus temperature of the liquid must be equals to 60 degrees. Now if this is unknown, we wouldn't be able to tell the temperature of the air. That's what this answer is trying to say. All right. So the cold junction is now placed back in ice. So ice is 0 degree. And the other junction is now left in the surrounding air. The thermocouple now gives a reading of 12 millivolts. So we will use this idea of a gradient. Now what does this mean? Okay. So initially, you see, initially we have 1.2. Sorry. So from here, 5.0 millivolts translate to 100 degrees Celsius change in temperature. Okay. So therefore, 1.2 millivolts is proportional to will be translated to what? Will be translated to 1.2 over 5.0 times 100, and we know that this is 24 degrees Celsius. Okay, so that means the change in temperature between the hot, so we have ice here, ice. So this is temperature is 0 degrees C, and then this temperature is what we don't know. All right, so that means T air minus T ice is equals to 24 degrees Celsius, and therefore since ice is equals to, since the temperature of melting ice is 0, so T air minus 0 is equals to 24 degrees Celsius. T air is equals to 24 degrees Celsius. Okay, 24 degrees Celsius. All right, so state and explain. So right now we have a thermometer. State and explain the effect of this fault on the thermometer. Now, how the thermometer works is this: when you have fire here, for example, all right, when you have fire here, you heat things up. What will happen is that it will cause these capillaries, they will cause the mercury or alcohol in this bulb to expand its volume, and then it start to fill. Because of the expansion, it start to fill up and go higher and higher as the temperature rise, because due to the expansion of the fluid. Now what we notice here is that, can you see the cross section here and here is not uniform? So not uniform, what does it mean? It means that at the start, so for example, so I give you an example. So let's say I give you a more extreme example. So let's say we have a cone cup. All right. So if I were to pour water in, all right. So initially, a same amount of water will cause a certain volume of water will cause it to rise by a height of, let's say, this height. But the next volume that I add in, right, it may only fill in this height. Okay. Although here and here is of the same volume. All right, so instead I explain the effect it has on this fault. So what can we tell? We can tell that as the temperature rise, right, the bulb will need to expand more to eventually fill this portion as compared to the initial part, because over here this is thinner, over here this is thicker. So this means that the thermometer is no longer accurate. So the thermometer is not accurate. But how not accurate? So what will happen is that you will notice that by right, maybe at a higher temperature it may reach here. Okay, if this capillary tube is uniform, but right now, because of this non-uniform capillary tube, you may not feel all the way to here. So towards the end, maybe it may be here. All right, so it means that it will under measure the actual temperature of the fluid, for example. Okay. All right, moving on. So in this question, it says that every element will absorb a certain set of electromagnetic wave based on the characteristics of each element. We can predict the element presence at any planet and stars in the universe. Yes, that's right. That's how we can tell whether Jupiter contains a certain percentage of hydrogen or helium, etc. And we can even look at our sun, the star, the only star in our solar system, to predict the amount of helium, hydrogen that is in the stars. Okay, so I won't spend too much time talking about this, but you can Google it and YouTube it to further understand what this is. So let's see. Calculate the frequency of the electromagnetic wave with the lowest frequency. Now, so EM wave, what's the characteristic of EM wave is that all EM wave has speed of light. Okay, all EM wave has, which is C, which is equal to 3.0 times 10 to the power 8. So calculate the frequency of the lowest frequency now. So we use our wave equation, V equals to F lambda. They want the lowest frequency. Okay, so F is equals to V over lambda, your wavelength. So how do we get the lowest frequency, right? Based on this, since V, the speed of EM wave is fixed, this is fixed, we need to choose this that is of the highest. Okay, simple math proportion. If this value is the highest, this will cause it to be the lowest. All right, so therefore from this table, let's see which one has the highest wavelength. So the highest wavelength is sodium, and therefore frequency is equals to the speed of light 3.0 times 10 to the power 8 divided by 720 nanometers. Okay, and then we can find the value. So is equals to 3.0 times 10 to the power 8 divided by 7.720 times 10 to the power minus 9. So you get a very big number, 4.16 times 10 to the power 14. Okay. Okay, so yeah, this is the answer. Hertz. 4.16 times 10 to the power 14 Hertz. Alright. The wavelength of visible light is between 400 nanometers and 700 nanometers. State the component or electromagnetic spectrum that are absorbed by sodium. Okay, so visible light is red, red to violet. Okay, so this is red, this is violet. Okay, now, and therefore if you have a wavelength of 720, which means this is before, okay, before red. And before red, if we recall the spectrum of EM wave, you'll know that before red is called infrared. Okay, so that's the answer. So state an application of this component. Now for infrared, typical application will be to use on remote control. Okay, to use on to send a signal to appliances. Okay, that's all. Pretty straightforward. All right, question 7 on light. So whenever you see this kind of question, I'm pretty sure it's light. Okay, so let's see. The diagram below shows two light rays R1 and R2 entering the bottles at different angles. The refractive index of water is 1.33, assuming that the thickness of the wall is negligible. Now, this is important because if without this statement, right, we can almost imagine that the light, okay, will light come in. This is my bottle. So this is my bottle. You'll come in the bottle. Oh, okay, it's a bit messy. So you have a bottle, and then you have your water here, right? I hope you can see the colors. Okay, so this part here is your glass. Now, when they say that the bottle, the wall, so this is the bottle wall. Now, since the bottle wall is negligible, we can almost assume that it doesn't exist. Okay, so straight away, the light rays only enters this way. Enter this ways and go into water. Alright, so let's find the incident angle. So how do we measure incident angle? Common mistake, incident angle is always measured from the normal. So this is from the normal. This, if you were to measure here, okay, so it's always measured from the normal. This is my normal to the light rays. Alright, if you are measuring somewhere else like here, then it is wrong. Okay, so this is my incident angle. So we'll use the Snell's law. Sine I over sine R is equals to your refractive index. So yep, so now we can find, so since the sine R is 30 and your R is 1.33, so sine I over sine 30 equals to 1.33. So sine I is equals to 2.668. No, sorry, not 2.66. 1.33 times 0.5. Okay, because this is from AMF, this is 0.5. So then I is equals to sine inverse 1.33. I is equals to sine inverse 0.638. 665. Okay, and then I is, you press your calculator, you get 0.665, 4.18 degree, and then 1.7, 4.17. Explain why R2 does not exit the bottle after the first refraction. Now, why is that so? So, whenever you see this, okay, so this is because over here in the bottle, this is water, all right, and then this is what we call dense. This part here outside is less dense. Less dense. So whenever light travel from dense to less dense, right, we need to check for one thing. We need to check for critical angle. Okay, we need to check for critical angle. So most likely this shows that there is a total internal reflection. Okay, this probably shows that there is total internal reflection, and so explain why R2 does not exit after the first refraction. So we know that this is total internal reflection. We say that since light is traveling from more dense to less dense, the incident ray at incident ray angle is greater than critical angle. Therefore, total internal reflection occurs. All right. So that is the only way that there will be a reflection. Okay, because like I said, this is dense, this is less dense. The air is less dense, the water is dense. All right. Figure 7.2 and figure 7.3 shows house filled with two different types of modified roof to allow sun ray into the house. The arrow indicates the direction of the sun ray at a certain point of the day. Explain why the modified roof in 7.2 is better than the roof in 7.3 in lighting up the entire room. You may draw on 7.2 and 7.3 if you wish to explain. So what happens is that let's say we have light ray coming here. Okay, light ray coming here, so it may just travel like this. Light ray may just travel like this. Okay, let me draw it in different colors. So light ray will just travel like this. This one may travel here. This one may, this light ray may travel somewhere like that. So can you see what do you observe is that the light only shines mainly this part of the house. And of course, if you understand ray tracing, by right the light will bounce and then you bounce around the house, but typically what we observe is that this part is brighter. Okay, brightest because the intensity is the highest. Now what happens when you put in a plastic filter with water? Now what happens is that let's see what happens. So let's say we come here. Okay, so the light ray come here, right? It may bounce, it may reflect. Can you see it's almost like a total internal reflection? It may bounce and then it comes out like this. All right, and then this light ray here, this light ray may be able to do this and exit here. And then the other light ray, this light ray, may be able to do hit this way and then bounce off like this. Okay, so can you see that this is a better design? So you can have this part of the house that is being lighted up. Can you see? Let's compare the two. Okay, you can almost see that compare these two, left and right. The one on the left is able to have the house more lighted up. Okay. So explain. So how we can. So by our drawing, we pretty much explain. So what we can say is that with the bottle, it allows light to be refracted in all directions to light up the house. Okay, now moving on. The boy stands in a room in figure 7.2. After some time, the boy feels warm. State the process in which the thermal energy is being transferred. So transfer of energy, and then we have, of course, we have the sunlight. Therefore, we know that the thermal energy is by this is the heat transfer via radiation heat. Okay, why is that so? Because the heat from the sun have to travel through space or vacuum to reach the point. Okay. Yep. So that's the only way in which the sun energy can reach Earth, and likewise also reach the point. Okay. So let's see question 8. Okay, magnets. The missing magnet poles and field lines around complete figure 8.1 indicating the missing magnetic poles and field lines around these two poles. Okay, the position of the neutral point, point X. Okay, let's do the neutral point first. So pretty obvious the neutral point is here. Okay, because there's no magnetic field lines here. Now, they want, so essentially you have two magnets. So this is magnet. So of course, north to south, and then let's complete the field line. So this one will come somewhere here. This one will come somewhere here. Of course, this one will come somewhere here. This one will come somewhere here. Maybe this one may go like this. This one might go like this. Okay, go like this. Like this. Okay, so we have completed the field lines. Okay, so remember, field lines always go from north to south. Okay, so north to south, right? The poles are all magnets, right? So let's say we have a magnet north south. What happens if we were to cut the magnet into half? Now, if we were to cut the magnet into half, it doesn't mean I have one side south, one side north. Okay, now interesting part about magnet is that let's say I have a bar magnet, I cut into half. This half will now become a south pole. This part will become a north pole. Very interesting. All right, so just a little trivial to let you guys understand how actually a bar magnet works, or what will happen if you were to cut a magnet into half. All right, so figure 8.2 shows a speaker. As current flows through the coil, material A is attracted and repelled by the permanent magnet, causing vibration in the cone. Suggest a suitable material for A. Now, a suitable material for A, so we have a coil. So we have a coil. Okay, and then this coil is of course connected. So this we are talking about this. Okay, will be connected to some form of like a AC current. Okay, AC current. All right. So which means that you can have current going in this manner, or you can have current going in the reverse direction. All right. So whenever the current goes in this direction, it creates a magnetic field, north, south, or when it goes the other direction, it can go north, south. So what happens is that, can you see you have a permanent magnet? So essentially what this means is that the coil is a magnet with a magnet, and then whenever that the current changes, right, it will attract. It will either attract or either it will repel. So it caused this cone to move in and out. So it creates sound wave. Okay, so it's like moving in and out because of the changing in direction of the current. Okay, so what is a suitable material for A? So what this means is that what we can do is that we can put this is what we call a core. Now a core, typically what we want to do is we want to use iron. So iron, why? Why iron is that? It's because iron is a soft magnetic material. You can easily magnetize or demagnetize it. All right. So explain why the suggested material in B is suitable. Like I already explained, because iron is a soft magnetic material, okay, which can be magnetized and demagnetized easily. Okay, that's all. All right. Let's see. Okay, a car is fitted with a parking system that warns the driver as how close objects are behind the car. Equipment on the rear bumper of the car transmits sound wave and receive the reflected wave as shown in figure 9.1. So you create sound wave like this, and then because it hit the walls, you reflect backwards. Okay. Now for parking system to work properly, the object must not be too near or too far from the bumper. The sensor in the parking system detects the time delay between the transmitted sound wave and reflected wave. Sensors can only detect a time delay between 500 microseconds to 1100 microseconds, which means that anything shorter than 500, it cannot detect. Anything more than 1100, it cannot detect. So calculate the minimum distance, okay, an object must be from the rear bumper to be detected. Now what happens is this. Okay, so there is a transmitter here. So there is a transmitter here. So the sound wave will travel this way, okay, and then it comes back. Now for sound to travel this way and come back, it needs time. Okay, it takes time to travel to the wall and come back. Now if this time is, in order for the transmitter to work, this time must be between 500 to 1100 microseconds. And therefore we want to find the minimum distance, which means we want to use the shortest time, which is this. Okay, why is that so? I will explain. So distance is equals to speed times time over 2. Why over 2? Because it's going there and back. Okay, so we want to use the shortest time, because if my time increases, then my distance will increase. Of course, hence we want to use the shortest time. So the speed of sound is 330 meters times 500 times microseconds divided by 2. And we will have divided by 2. Okay, we will have 0.0825 meters. Okay, 0.0825 meters. All right, which is actually about 8.25 cm. Okay. Now the equipment on the rear bumper is replaced with another equipment which transmit and receive radio wave. The sensor of the new equipment can detect the same time delay as a sensor that uses sound wave. By repeating the calculation in part A for the new equipment, determine and explain which equipment will be more helpful in helping the driver park. Now, so like I said, the shortest time delay that the sensor can detect is 500 microseconds. So let's say we were to use a radio wave. So radio wave, right, have a velocity of 3.0 times 10 to the power of 8. Now, in that case, let's find the minimum distance. So distance will be equals to if let's say in this case we use radio wave, let's find the minimum distance before the car can detect the object. All right, so it's 3.0 times 10 to the power 8 times 500 times divided by 2. I think you will get a very big answer. Okay, so I don't think this is very practical. Oh, okay, wow, this is not practical at all. This is almost like let me see, 82.5 km. So you can only detect by the time you have already crashed into the wall. To give you some perspective, from Tampines to Jurong to Tuas of Singapore is around 50 kilometers. So uh, you can't use this new sensor to work. So how do we explain this answer? So we will say that based on the new calculation, based on the new calculation, the radio wave sensor can only detect the wall when it's 82.5 km away. So this is clearly not practical. Okay, so hence not helpful in a typical parking situation. Okay, so you are not gonna park your car when you are like 82 km away from the wall. Typically, a driver will the distance of the car to a wall for a typical parking scenario is maybe around 2 meters to 1 meters, or sometimes even shorter. It could be a very small gap like 30 cm, etc. So this is really not practical at all. Okay, 82 km is really not practical. Okay, let's take a look at the next question. So this question is definitely on the topic of electricity. So let's see. So we have a voltage of 200 volts, and then they are connected in, you can see these are connected in parallels. Okay, so lamp 1, lamp 2, lamp 3, they are all connected in parallel. Ammeter is connected there. Okay, so now so let's see what happens. So when ammeter in the circuit shows the current is 0.4 ampere when only lamp 1 is switched on. So let's say when we switch on like this, the current is 0.40. Okay, when you switch number 2 on is 0, it will be 1.9, and then when you switch on number 3, it will be 7.60. Okay. Now calculate the resistance of lamp 3. Now, so how do we calculate this? Now, so how much current is being drawn here? We need to know. We need to know how much current is being drawn here. Current going through lamp 1 is 0.4. Current going through lamp 2 is not 1.9. Because when both switch 1 and 2 are on, which means that current coming through is 1.5. Okay, current, when all 3 lamps are used, the current is 7.6, which means that the sum, you see, this, that means that the current is 7.6. If 0.4 goes here, 1.5 goes here, the remaining will be here. So this will be 7.6 minus 0.4 minus 1.5, 5.7 ampere. Okay, so this is essentially what we mean by conservation of charge. The current in must be equal to the current out. So the current in to this node must be equal to the current out. Okay, so the current, although the current is not the same in all circuits, but the current into this node, and then you see all 3 come back, okay, must also be 7.6. Right, so which means that this is 0.4, this is 1.5, and then this is 5.7. So to find the resistance of lamp 3, so what is my PD across lamp 3? PD is, since this is parallel, PD is 200 volts. Therefore, PD is equals to IR. So R is equals to PD over I. So 200 over, what is my I? 5.7. So we get, so R is equals to 35.08 ohms equals to 35.1 ohm. Okay, 35.1 ohms. Alright, calculate the weekly cost of all 3 lamps that are in use at the same time for 110 minutes each day. The cost of 1 kilowatt hours of energy is 22 cents. Okay, so weekly cost or at the same time for each day. So first of all, let's find the power used. Okay, the power used. So the power used is equals to power equals to I P. Right? So the total current is 7.6. The voltage is 200, and then the power will be, okay, 1520 watts. Now, because this is in kilowatt hours, so I want to leave it in kilowatts. Oh, sorry, kilowatts. Okay, 1.52 kilowatts. Now, that is only the power. So the energy use, how do we calculate energy use? The energy use will be equals to power times time. Now we have the power in kilowatts, but take note, because you want in kilowatt hours, and in each day is used for 110 minutes. So how much time do we on it on a weekly basis? So in 1 week, 1 day, 110 minutes. 1 week will be equals to 110 times 7. 110 times 7 equals to 770 minutes. Now we still cannot use 770 minutes because in this case the unit of power is in terms of kilowatt hour. So we need to convert this into hours. So it's also equals to 770 divided by 60 to, because 1 hour has 60 minutes. So 770 divided by 60 12.83 hours. Okay, so power energy use will be 1.52 times 12.83 hours. So times, okay, it will be 19.5 kilowatt hours. All right, so in 1 week, okay, so this is in 1 week, energy use in 1 week. Okay, so how do I find cost? Cost will be equals to energy use times price. So it will be 19.7 times 0.22, 4. Okay, so it will be approximately $4.29. Okay, dollars 4.29. All right, this is pretty straightforward. Okay, now finally on section B of the database question. So let's take a look at what kind of information we have. So in many countries where average temperature can vary between -3 degrees to 19 degrees Celsius, solar energy is used for heating up the interior of the house. Solar energy is absorbed by cool water running through coil pipes located on the rooftop as shown in 11.1. Warm water is then stored in the insulation tank, as shown in the 11.2. In passing through the radiator, the water in the pipe will reach the same temperature as the required indoor temperature in the house. After moving through the electrical pump, the water will reach the same temperature as the outdoor temperature. Okay, so let's read on further and then we will analyze this question further. Data relevant to the usage of the heating system is given in a box. Temperature of warm water 45 degrees Celsius, specific heat 4.2 times 10 to the power 3 joules per kg degrees Celsius. Power of the rooftop solar energy collector 12 kilowatt. Average thermal energy required to maintain the indoor temperature of 25 degrees Celsius for 24 hours is 200 megajoules. So what this means is that, okay, so and then of course in 11 we take a look at this table here. You have the outdoor temperature of France is 14, and then the average daily sunshine is 7.5 hours. So let's read the question further before we analyze the entire question to find out what exactly do they want. The heating system is installed in a house in France. Determine the average mass of water required daily to maintain the indoor temperature of 25 degrees Celsius. Okay, so essentially let's go through the question over again. So and then this paragraph here is quite important. So what happens is that, okay, we have hot water. Okay, so hot water will be here. Okay, so the solar energy will cause the cold water to become hot water, and then hot water is stored here. So in hot water, out will be 25 degrees Celsius. Now why 25 degrees Celsius? If you read requires the indoor temperature to be in the house. So the water in the pipe will reach the same temperature as the required indoor temperature. So therefore, the water in is 45 degrees, and then the required temperature of the house is 25 degrees. Okay, and then thereafter, after the electric pump, moving through electric pump, the water will reach the same temperature as the outdoor temperature. So in this case, right, after the pump, this water that is 25 degrees Celsius will further cool by the environment. So in this case, we are looking at France because the question wants France. So the outdoor temperature will be 14. Okay, so 14 degrees Celsius. All right. So with that, we can calculate the mass. We can start after we have analyzed this, we can start working on this question. Determine the average mass of warm water required daily to maintain the indoor temperature of at 25 degrees Celsius. Now, what this means, so this is the house. This part is the house. And where do the house get the energy from, or how do we heat up the house? Basically, it's from the warm water. So the warm water will get cooled down from 45 degrees Celsius, and then it will eventually become 25 degrees Celsius. So heat is giving out through the radiator, and then as heat is being given out, the temperature will drop from 45 degrees to 25 degrees Celsius. Okay, so how from here we are able to calculate the amount of warm water that is required, because in this question it says that the energy required to maintain the indoor temperature for 25 degrees for 24 hours one day is 200 megajoules. Therefore, we can use this equation, Q equals to mc delta T. Now, why can we use this equation is because essentially, as the water reduces its temperature, we are able to calculate how much heat is given off by the water. And in this case, in order for us to maintain 25 degrees Celsius, we will need 200 megajoules. 200 megajoules of energy. Now, how much mass we don't know, we leave it here. Specific heat is 4.2 times 10 to the power 3. Delta T, what is my delta T? Delta T is in is 45, out is 25. So it's 45 minus 25, and eventually we can calculate this. So, and with this we can calculate the mass. So 1 second, 200 megajoules divided by 4.2 times 20. Okay, so we get the mass to be 2,380 kg. Okay, so now calculate the total solar energy required to heat up the cool water daily to maintain the room temperature. Now, this is a bit misleading. So what happens is that at the solar rooftop collector, what happens is that the temperature, okay, so because after the pump, the temperature of water becomes same as the outdoor, which is 14 degrees Celsius. Now, in order for you to heat up the room, you need the solar panel will need to heat the water to 45 degrees Celsius, and therefore we are calculating how much energy is given by the solar panel in order to heat up the temperature from heat up the water from 14 degrees to 45 degrees. Okay, so calculate the total solar energy required to heat up the cool water daily to maintain. So total solar energy will be equals to same thing, Q equals to mc delta theta. Now, we already know we require 2,380 kg of warm water in order to maintain the room or maintain the house at 25 degrees. So Q will be equals to 2380. C is still the same, nothing changed, the specific heat. Now in this case, my delta T will be 45 minus 14. Okay, because the solar energy is required to increase, okay, to increase from 45 degrees to 14, from 14 to 45 degrees, and then we can calculate. So 2380 times 4.2 times 1000 times 45 minus 14. Okay, so divide by 10 to the power 6. So it's about 0.8 megajoules, okay, which is about, let's round it off, megajoules. megajoules. Alright, so 310 megajoules. Alright. Calculate the time needed by the solar collector to absorb the amount of solar energy calculated in part 2. So in this case, we already know that the solar energy collector is able to collect 12 kilowatts of power, and from there is pretty straightforward. Energy is equals to power times time. Therefore, time is equals to energy over power. And we have 310 megajoules over 12 kilowatts. And then we can find the time, okay? Times 10 to the power 6 divided by 12, 123. So you get about 3 seconds. Now take note, this is in seconds, right? Because the SI unit of time for power is in seconds. Now, so let's change this to hours. So this will be equals to equals to 7.175 hours. Okay, 7.120 hours. Okay, 7.20 hours. This is my answer. So how do you get 7.175? You just use this divided by 3600 because 1 hour has 3600 seconds. Essentially, because we have 60 minutes and each minute has 60 seconds. So 60 times 60 will give you 3600, and then from there we can calculate the time in hours. Okay. So with reference to figure 11.3, explain why heating system is not able to maintain the indoor temperature at 25 degrees for Fiji. So let's take a look at Fiji and how come in the first place why in France we can maintain the temperature. Now you see in countries with season, right, they do not have like a 12 hours sunshine daily. Not like Singapore. In Singapore is pretty clear that we have 12 hours of daylight and then 12 hours of nighttime approximately. But in countries where you have seasons, okay, so it's not necessarily true that they will always have 12 hours of daytime and 12 hours on nighttime. Alright, the amount of sunshine will change depending on the season. So but in this particular month in May, right, for Fiji only has 4 hours of sunshine, which means you only have 4 hours of sun to heat up the water, and in order to maintain 25 degrees Celsius, which is not enough. How much do we need? We need 7.2 hours in order of sunshine in order to maintain the 25 degrees Celsius, and therefore the answer would be in Fiji there is only 4 hours of sunshine. Okay, there is only 4 hours of sunshine, hence it is not sufficient to collect enough solar energy to maintain the house temperature of 25 degrees Celsius, as it will require 7.2 hours of sunshine. Okay, right, essentially what I'm trying to say is that in order for us, minimally we need 7.2 hours of sunshine in order to maintain this amount of energy collected in order to keep the water at 45 degrees Celsius. Okay, suggest a material for making a coil pipes at the rooftop and explain the reason of your choice. So basically this is the coil pipes. Alright, so what do you think the material is? Now in this case we want the metal, we will use that we want a metallic pipe at the roof. Okay, why is that so? Because metal is a good conductor of heat. And so what? So why good conductor of heat is required at the rooftop? Because so that the heat from the solar collector can be easily transferred to the water to heat up the water, to heat up the water for warming the house. Okay, so next question, question 12 is on circuits. Alright, so we basically have variable resistor connected to a lamp in parallel together with a fixed resistor at 200 ohms. Okay, so first part, state Ohm's law. Oh, okay, so the definition of Ohm's law is the resistance is directly proportional to the the current through the resistor is directly proportional to the potential difference across it. Okay, provided that no physical change to the resistor. Okay, this one you can check it up on the textbook and you will get the answer. Explain why the filament does not obey Ohm's law. Now if you take a look at this, right, basically R is equal to V over I, which means that your resistance is the ratio between your potential difference and I. So in this graph, it clearly shows that the ratio is not fixed, because if it's fixed, the gradient should be the same. But if you see here, the gradient is changing, it's decreasing. Okay, it's changing, and hence we clearly that this filament lamp does not obey Ohm's law. But why? So the reason why is because as the PD increases, okay, this increases the temperature. Okay, this increases the temperature of the filament, which changes the resistance of the filament. Okay, so that's how it is. Using figure 12.2, state and explain the change in resistance when the potential difference is increased. Now there's two ways to look at this. You can either use the ratio method, or we can use the gradient method. And in this case, I like to use a ratio method because it's more straightforward. So what we can do is that we use here, and then we see that, okay, so at this, okay, we'll use this point here. Okay, we'll use this point, and then so at this point, my resistance is equals to potential difference 4 over 0.06, which works out to be 66.67 ohms. And then maybe we can use another point here, so my resistance is equals to 1 over 0.03, 1 divided by 0.3, 33.3 ohms. Okay, so so in this case, we can say we can easily answer this. We will say that the resistance of the lamp increases as the PD increase. So we only state, this is only state, we need to explain. So why is because we can use a ratio based on the graph. The ratio between the PD and current increases as the PD increases. Okay, essentially we are just talking about the increase, and then we are talking about the resistance is increasing. All right. Okay, the current and potential difference for the lamp can be changed when component X is being adjusted. Name component X. So let's take a look. So this is pretty obvious. This is, by now you should recognize this symbol. This is what we call a variable resistor. Okay, explain how the component X can decrease the current through the lamp. Okay, so what happens is this. So let me erase this. So what happens is that as so this is a variable resistor. So when R increases, all right. So when R increases, what happens is that the PD across this point increases, but it will cause the PD across here to decrease. Okay, essentially this is what we call like a potential divider scenario, where the potential, the EMF, okay, is split into two parts. Okay, split to here and split into across here, across the variable resistor and across the parallel of this length. Okay, so that's how I already explained. So just putting it in words, explain how component X can decrease the current through the lamp. So when the resistor of X increases, this decreases the PD across the lamp. Okay, hence not hence, given that current across lamp is equals to PD divided by R lamp. Okay, so if PD decreases, the current across the lamp decreases. Okay, so I hope it's clear. So if like I said, I repeat myself again, because I increase my resistance, the PD across so let's call it PD1 and PD, so let's call it V1 and then let's call this V2. So EMF is equals to V1 plus V2. Now because when I increase my R1, because when I increase my resistor of across the variable resistor, V1 increases, and given that your EMF has to be the same, V2, the PD across the potential difference across the lamp, will have to decrease. And as such, if my potential difference across the lamp decrease, okay, if V2 decrease, the I will definitely decrease given. Okay, so you can take a look at this table here. When my PD is reduced, okay, my current also decrease. All right. Okay, the potential difference across the lamp is 2.5 volts. Determine the electrical current through the lamp. Now in this case, you can only use the graph to find the current, because this is not the ohmic. This lamp does not obey Ohm's law, or what we call is not an ohmic conductor. So in this case, we will use 2.5. 2.5 is here. We trace up, we look here, we look across. Okay, so the answer is 0.05. 0.05, easy. Okay, ampere. All right, calculate the electrical current through the 200 ohms resistor. Now in this case, since this is in parallel, since they are in parallel, okay, if V2, if the PD across the lamp is equals to 2.5, the PD across this is also 2.5 volts. Okay, and therefore we can find, so current I is equals to PD over R. So what is my PD across the resistor? We already established that the PD across the resistor is 2.5. It has to be the same as the lamp because they are in parallel, and then the resistor across the resistor is 200 ohms, so it's 2.5 divided by 200. 2.5 divided by 200, we get 0.0125 ampere. Okay, 0.0125 ampere. All right, either or time. Okay, so let's see. Figure 13.1 shows an incomplete structure of a direct current motor. A regular coil ABC is connected to component X. The coil is placed between two permanent magnets, and the coil is observed to rotate clockwise. So clockwise, so this thing will rotate. This thing will rotate clockwise like this, spin up like that. Then after that, we have magnetic field that is flowing this way. Okay, what does it mean? It means that if it's going clockwise, it means that on the line AB, there's a force. Okay, there's a force. Sorry, wrong side. There is a force downwards, force, and then on this end, on the line CD, there is a force upwards. Okay, so because of this downward and upwards, it creates like a clockwise moment. Okay, it spins this way. All right. So from there we can determine. From here we can determine the direction of the current. So we will use Fleming left-hand rule. Okay, Fleming left-hand rule. So Fleming left-hand rule shows that this is, let's say, let me try to draw it out for you guys. Okay, so this is right angle. Okay, so using Fleming left-hand rule, right? So this is father. Let me try. Okay, so you have your magnetic field, you have your force, so your current must be here. Okay, so right, can you see if let's say, okay, let's put it beside and compare. Right, the magnetic field is towards the left. The current will have to be pointing towards us because the force is downwards. Okay, so this is, we will use this, and therefore state the direction of current flow, explain how the rotation direction of the current is determined. Okay, so the current is going from B to A, and likewise we can also say that it's going from B to C to B to A. Okay, so essentially it's going this way. Okay, all right, like this. So explain how the direction can be determined. So we can only use Fleming left-hand rule to determine the direction of the force, the magnetic field, or the current. So using Fleming left-hand rule, okay, using Fleming left-hand rule, the magnetic field is towards the left and force is down on AB. The current will have to flow from B to A. Okay, it needs to flow from B to A in order to achieve to produce a force downwards. Okay, a complete structure of the DC motor, on figure 13.1, complete the structure of the DC motor by drawing the external circuit comprising of carbon brush and a direct supply and a switch. Okay, so let's draw this. Okay, let me shift this away. All right. Okay, so we will connect this. So take note of the direction of the current. So the current is coming out and in. Okay, so it will come out, come in. Okay, and then so therefore Okay, so maybe we need to draw something else. So we need to draw the brush. Okay, we'll draw the brush. Okay, and we draw the brush. Okay, so current will go this way from positive to negative. So the current will go this way. Okay. Alright. Name the component X and clearly how X ensure that the coil continuously rotate in the clockwise direction. So this thing, this X, is what we call the X is the split ring. Okay, so what does the split ring do? The split ring ensures that the direction of the current will reverse every half rotation. Okay, so this means that the force acting on AB and DC will change every half rotation. Okay, so with that, right? Okay, so with that, this then allows the moment to remain consistently in clockwise manner. Okay, the coil ABC rotates faster in the reverse direction. Suggest the changes made to the DC motor to achieve this. Oh, strange. The coil rotates faster in the reverse direction. Okay, so one way, so how can we make it rotate faster and in reverse direction? Suggest changes made to the DC motor to achieve this. So one obvious way is that use a higher EMF cell to power the motor. And then the next one, so but this part here only suggests that it rotates faster. So what else? How do we reverse the direction? Okay, change the polarity of the cell connected. So this will change the direction of the current through the coil. Okay, so essentially basically what I'm trying to say is that instead of here positive, here negative, right, we change, okay, just for illustration, So what we do is, instead of one cell, we put two cells, and then now it's positive, negative, so the direction of the current will change. Okay, so therefore it changes the direction of the rotation as well. Okay. Okay, last question. Okay, so this question will be on static electricity. All right. So from the looks of it, let's do the analysis. Now, state the net charge on the sphere. All right. So let's see. Okay, we have an electric force in this direction with here tension. All right. So now in this case, it's quite obvious that how do you have a force that is this way, which in this direction, which means that can you almost feel that in this diagram, this ball is being repelled in this direction, and therefore in order for this to happen, this has to be a positive charge. Okay, because like charges repel, so this has to be a positive, this is positive, so like charges repel, so they push each other. Okay. All right. There are three forces acting on a sphere. The tension is 5 Newton. In the space below, draw a vector diagram with an appropriate scale to determine the magnitude of the electrical force. Okay, now I don't have a ruler. I can't draw things in scale, but I can roughly sketch out how it will look like. All right. So tension of the string is, so let's draw the free body diagram of. So let's start with the free body diagram of the sphere. We have this that is 20 degree, and then we have this, which is the W, the weight, and then we have this, which is okay, which is perpendicular. Okay, so therefore what we can do is we start off like this. So we have this, draw like this. All right, so sorry, not really to scale, but you get my point. So this will be 20 degrees, and then we say that this is 5 Newton. All right, and then we have this is the weight, this is the weight, and then you have this is the electrical force. All right. So but they want a vector diagram, which means that they need like a triangle. So how should we draw it? So I will roughly show you how it's done. So here, let's shift it one side. Oh no. Let's put it back. Okay, so essentially what we can do is this thing here. Okay, you can pull it out, for example, and then here we can pull it out, put it here, and then here. So this is the diagram. Okay, so in short, the final answer will look like this. It should look like this, but you need to draw it in scale. Okay. Okay, so then you say that this is 20 degrees. Now, make sure that the arrows are all in the tail to tail. Okay, so in hold on, wrong one. So you must make sure that all the arrows are in the same direction, which means, can you see that this is here, This arrow here is pointing to the tail of this arrow. This arrow, the head is pointing to the tail of this arrow. So they all are in a way same direction. Now, when you have arrows that are in same direction, for example, like this, okay. So this is what I call same direction, because you can almost see that they can go in a loop. You can, if you follow the arrows, okay, you can like literally run around the vector. Now this means that the net force is equals to 0. All right. So this is what it represents. Okay, because you see, how do I know that the net force is equals to 0? Suspended, okay, by a non-conducting string. Suspended means stationary. Okay, stationary also means no net force. All right. So yeah, so then after that you can, based on your vector diagram, you can measure the length here, and then from the length here you can measure the length here to find, and then you find the length here. So you find the length here, you find the length here. Based on this length here, with the scale diagram, you are able to find the magnitude of the weight and electrical force. Okay, state the force that is in the action reaction pair of the weight of the sphere. Say the force that is in the action reaction pair. Action reaction pair. Action reaction pair. State the force that is in the action reaction pair of the weight of the sphere. Action reaction force. Action reaction force. Okay. It is also weight. Sorry. It is also the gravitational pull. Pull by the sphere on Earth. Okay, which means I have a sphere and we have Earth. Earth is attracting it, but at the same time, Earth is also being attracted to the sphere. Okay, so every object, every matter in this world has gravity. Okay, which means that as much as Earth is attracting you to Earth, you are also attracting Earth to you. So that forms an action-reaction pair. Okay, so part B, the sphere is Earth and charge is still held near the plate. Is still held near as shown in figure 13.3. Describe the movement of charge in the sphere when it's being earthed. So what happens is that initially this is a positive charge. So let's analyze what happens. So when you're earthed, the electrons, okay, bear in mind only electrons can move. So the electrons will come here. Okay, so electrons will come into the positive charge, and then what happens? So the electrons from the Earth will travel to the sphere. Okay, right? You don't, please do not say that positive charge go to the Earth. No, there's no such thing. Positive charge cannot move. Only negative charge can move, because electrons can move. All right, protons can't really move, so to speak. The Earth is now removed. So now that we remove, describe and explain the change in position of the sphere after it is earthed. So what happens is that when you earth it, the electrons comes here. So you have negative charge and positive charge together. This becomes, so what happens is that this becomes neutral. Okay, this is neutral, no charge, no net charge. Okay, so once you remove the Earth, right, it becomes neutral. The sphere so will become become neutral. Now, so, but what happens? Neutral and positive. What happens to neutral and positive? Neutral and positive will attract. Why? Okay. Will become neutral and be attracted to the positive plate. Okay. So what happens is because it's neutral, right? This positive charge here, right, will induce the charge, okay, the negative charge to one side. Okay, so you have a negative and you have a positive, they attract one another. Okay, the charge is moved far away from a sphere. Draw how the charge will be distributed. Okay, so I already gave the answer because of the electro induction. So there will be negative charge on the right hand side, assuming the positive charge is here. Okay, and then you will draw the positive charge here. Take note, you need to make sure that the number of charge here is equal. So if you have 4 here, you must have 4 here. Okay, so that's it for this paper. So I have essentially run through the entire paper from start to finish without actually looking at the answer. So if you still like this kind of content, please stay tuned. I will continue to upload this kind of I will continue to work on more papers, and then and explain how we get answers along the way. I hope this will help you in your exam, and please stay tuned to TissueY channel. There will be more content coming up. Okay, all the best.